All right, let's continue our lectures. And before we start talking about vectors, we're going to continue our talk about motion, and we're going to wrap up our talk about free fall with actually taking air resistance into account. So let's just take an example. In our discussion about free fall, we always talked about objects falling under the influence of gravity only. So if we were to draw a picture of an object falling a certain height, the force that would be acting on it would be its weight, the force due to gravity. And, since weight doesn't change as something falls through the air on Earth, not significantly anyway, that weight would stay constant anywhere during the path of its motion. So their net force would be pulling it downward, making it accelerate. And so when something is in free fall, the position graph, y versus t, would be a parabola getting bigger and bigger and bigger in the negative direction. So it starts out flat and it gets bigger and bigger and bigger in the negative direction. And the velocity graph would start at zero velocity, and the velocity would get bigger and bigger and bigger in the negative direction, and it would be linear. And the slope of that would be the acceleration of gravity, negative 9.8 meters per second squared. But when we hit free fall, what happens is that we end up taking into account air drag. And air drag, as you can see in this picture, air drag acts upward on the object. So these guys have weight acting on them, but they also have air drag, F of the air, acting up on them. And it turns out that as they increase their speed, the force due to air increases. And as you can see in this picture, if they increase their surface area, that also increases the force due to air. Okay, so as they move, this force will increase. So let's look at that in an applet. Let me find it. Okay, so let's just take a look at this particular applet. And what we're going to do is we're going to take this anvil and we're going to set it, we're going to look at it, and we're going to let me just reload the page. All right. So as the object falls, it has air drag and it has weight on it. Notice that at first the weight is much bigger than the air drag, but as it increases its speed, its air drag increases. And eventually, if you look at the speedometer, when the air drag reaches its weight, it is now in equilibrium. The net force on it is zero, which means that it will no longer accelerate. This is what we call terminal velocity. So when an object is falling, the force that causes it to fall is gravitational force. And as it falls, the air drag increases until they are equal and opposite. So they cancel each other out. So the net force is zero acting on it. So there is no more acceleration, and it is at a constant speed. So if we just look at what's happening and we just take the just look at the speed. As the object falls, it accelerates and gets faster and faster until it reaches a constant speed. So you can see this area is acceleration, and this area on the position graph is constant speed. The velocity graph is linear, and then, so this is acceleration, and this is constant speed. And then you can see that the acceleration is at first very high. It's close to 9.8, and then it decreases over time because the net force is not equal to the weight anymore. It's a little less than that. And then it levels out and is zero acceleration. So that's it for terminal velocity. It's pretty easy. Now, a couple things to remember is, yes, bigger objects fall harder. The reason they do is because it takes them longer to reach terminal velocity. So if you drop a metal ball versus a styrofoam ball, the styrofoam ball may have less mass, but the reason it reaches terminal velocity first is because it has less mass and thus less weight. It doesn't have to fall for very long until these conditions are met, where FA is equal and opposite to FG.